let's continue our journey of artificial intelligence, and our next stop is Bayes nets. So last lecture we started looking at probabilistic models, and the one thing to keep in mind, and that will be even more centered in this lecture here, is that any model we build is an approximation. It's an approximation that hopefully captures the most relevant parts of the real world for the problem we try to solve, but typically not everything, because that would make for an intractable model to work with. So the one quote to keep in mind here is that all models are wrong, but some are useful. All right, so what do we want to do with the probabilistic models? That will in turn decide what makes a model useful or not. Well, we want our agents to reason about unknown variables given some evidence. So one application would be diagnostic reasoning. Is our model suitable for, given some measurements of symptoms, let's say, back out the likely causes, maybe the disease somebody has? Prediction. This is causal reasoning. Let's say you observe the world today. Is our model a good model to predict what the world might be like tomorrow, day after, and so forth? Then in the future, what we'll look at is something called value of information. And the idea there is that we'll decide which variables to measure based on some quantity called value of information. And that'll tell us how valuable it is on expectation to go out and measure a certain quantity. And that'll tell us something about whether we're willing to pay, for example, for that measurement, or we're not willing to pay for that measurement, and how much we might be willing to pay. Okay, so I said the models we'll use will be approximations of the real world, and the type of approximation we'll be working with will be independence and later conditional independence. So what is independence? The basic concept is for two random variables. If you have a distribution over two random variables, x and y, and for that joint distribution, for each entry in that joint distribution, we have that probability of x and y jointly is equal to the product of the probability for x with the probability for y, and that is true for all entries, then x and y are independent. Looking at this equation here, one consequence that we'll take advantage of in the future is that what that means is that now you can write your original distribution, rather than as a joint distribution, as the product of two distributions that are now only over one variable. Another way of writing independence is that x and y are independent if and only if this statement holds true for all x and y. This is saying that for all x and y, the conditional distribution for x conditioned on y is the same as the marginal distribution for x. What that means is that observing y doesn't change your distribution for x. Why are they the same? And why does this one imply the other one? Well, and same the other way around. You can just fill in the definition of conditional probability. Px given y is the same as px comma y divided by py. And we say that has to be equal to probability for x. Well, multiplying both sides with py gives us px comma y equals px times py. So this little derivation shows that both ways of defining independence are equivalent. There is a third way of defining independence between x and y. It would be to swap the roles of x and y. It would be to say for all x comma y, probability of y given x equals the probability of y. This is the shorthand notation for x independent of y. In practice, will distributions have that property? Real world distributions probably not, but we might approximate them by a distribution that does have the independence. And so here is a set of 4 random variables. You could ask yourself the question, what would be a reasonable approximation in terms of assuming some independence here? You could say, well, maybe cavity and toothache are independent of weather and traffic. You could, of course, argue that's not always the case. We talked about that last time, but it's a reasonable assumption. For many situations that you try to reason about, this will be a fine assumption. So how do we verify independence? Let's say somebody gives you a table, this table here, temperature and weather, and you're asked the question, are T and W independent? Well, one way is to just look at the definition. That means building the marginals for temperature and weather, which we saw last time how to do. Once you build the marginals, then you can multiply these marginals together to build the joint based on a product of the marginals. So we will build PT times PW over here. That gives a new table. Every entry here is built by multiplying together an entry here and an entry here. For example, hot and sun 0.3 comes from hot here and sun here. Multiplying them together gives 0.3. This is a new joint distribution. In this new joint distribution here T and W are independent by definition because we defined it by multiplying together two marginals. Those marginals came from this joint distribution over here. If P1 and P2 are identical, then our conclusion is that T and W are independent. If P1 and P2 are not identical, then we know T and W are not independent. So looking at these tables, already the first entry is different. Once one entry is different, we know the independence is not true, because it's not true for all T and W. And so T and W are not independent for this joint distribution here. Okay, that's how we can check this. Let's say we have a lot of distributions. Let's say they're all coin flips. Each one of them has a 50% chance, heads or tail. You multiply them all together to get a joint distribution over all variables. This will have 2 to the n entries. One entry for each possible combination of each of these variables. So while these tables are just of size 2, and then this is n, so effectively you have 2 times n. Over here you have a table of size 2 to the n that encodes the same information just in a much less compact way. You can always do this, and you can also start seeing here why we might care about finding the independencies, because this representation here is very expensive. This one here is much cheaper. So here's a reason why you might want to use independence, is because you get a much more compact representation of your distribution over many, many variables. Now, independence is a very strong assumption, and we'll actually move away from that, because if you think about it, the problem with independence is that your distribution falls into pieces. If things are independent, observing one variable doesn't tell you anything about the other variables. And so that's exactly what we're not interested in. We want to build models where if you observe one variable, it tells us something about the variables we haven't observed yet. So independence is too strong an assumption to be a good assumption to be working with in most cases. So we'll soften this assumption a little bit, and we'll use something called conditional independence. Just to annotate the random variables here, this is fire, this is smoke, and this is alarm. And to give you some intuition of what we'll be getting at, what we'll be getting is that there's some relationship here where fire causes smoke, smoke causes the alarm to go off, and even though the alarm going off is not independent of whether there is a fire or not, once you know whether there is smoke or not, you can already tell a lot about whether the alarm will go off or not. And somebody telling you whether there is fire or not, once you know there is smoke, knowing that there is fire is not giving you any new information about what will happen to the alarm. So in some sense, the effect of fire on alarm is indirect and is mitigated through smoke. And how we'll encode that is we'll say smoke makes alarm and fire conditionally independent. Okay, let's start building this up. So we'll go back to the toothache domain. Let's say you have potentially a toothache, there could be a cavity, and the probe of the dentist robot could catch on to your cavity. That's a joint distribution over 3 random variables, each of them binary. Then you can start looking at properties of this distribution. Let's say we look at this entry over here, conditional distribution, and we look at the probability of there being a catch, given that there is a toothache and there is a cavity. And we find out that that's actually equal to the probability of there being a catch, given that there is a cavity. So here we just have cavity, here we have toothache and cavity. Why could that be the case in our model? Well, the probe really latches on to the cavity. And it's the cavity that might cause both toothache and being caught. But whether you have a toothache or not doesn't really influence whether the probe gets caught once you know there is a cavity. Let's say this is also true when you don't have a cavity. The probability of being caught is given toothache and no cavity is the same as the probability of being caught when there's just known that there is no cavity. Again, that's a reasonable assumption. Let's say both of these assumptions are true. These are properties of the distribution over 3 random variables. If you write down a distribution over 3 random variables, you can check that, because you can compute these entries and check whether they satisfy this assumption or not. You can force them to satisfy the assumption potentially. If you're willing to make this assumption, then we'll write this as the conditional distribution for catch given toothache and cavity is equal to the conditional distribution for catch given cavity. What's the difference between these two? Here we just have the random variables, whereas up here we have the instantiations in the back. And by just having the random variables here, it means our notation implies that this means it is true for all possible instantiations of these random variables. Okay, that seems reasonable. Probability of catch is independent of toothache once you know there's a cavity or there is no cavity. Equivalent statements to the one above. So this is the one we've been working with right here. Equivalently, we could write that the probability of toothache comma catch given cavity is the same as the probability of just toothache given cavity times the probability of catch given cavity. Remember the definition of independence where we said x and y are independent if and only if for all x and y, px comma y equals px times py. This looks the same. The only thing that happened here is that we have now an additional variable z, and the variable z is just appearing everywhere in the back. There's a given z, given z, given z. Now, of course, it'll be for all z, and we'll write x independent of y given z. So conditional independence can be seen as the same thing as independence, just you carry a conditioning thing in the back of your expressions, and everywhere you condition on the same thing, in this case z, or cavity. And then this one up here was just the other way of writing the assumption of independence. The other way of writing it was that x independent of y, if and only if for all x comma y, the probability of x given y equals the probability for just x. We're just adding a z. We're now saying y comma z, x given z. So we condition on, in addition, on z, and now we have conditional independence. So fundamentally there is nothing that has changed here. There's just now everywhere conditioning on this additional variable, and then we call it conditional independence. And we would write that in the back here as conditioned on z. And of course this now would have to be true for all z also. So that's the difference between independence and conditional independence, whether you carry around something that you're willing to condition on. But as you can see from the example, the assumption becomes a lot more realistic. Conditional independence is a lot more realistic to assume than plain independence. So plain independencies are pretty rare. Moreover, when they're true, typically they don't lead to interesting probabilistic reasoning models because observing something doesn't allow you to infer something about other variables. Conditional independence will be the building block for the representations we're going to build. we say x is conditionally independent of y given z, if and only if this expression holds true. So again, if you look at this, z is appearing everywhere in the back. If you ignore that, you get the same expression as you had for independence. The key observation is that by adding z, you get a much more realistic assumption than the absolute independence assumption. Equivalently, we have this expression over here, and we just re-derived that on the previous slide. Our notation is this now. Any questions about conditional independence? Lots of questions. Good. Over there.
Does it mean like if I don't have condition x and y it's not independent?
Yeah, so that's a great observation. The question in some sense is, if this is true over here, does that imply x independent of y? All right? And the answer is no. Typically not. And it's even true, as we'll see, that x independent of y doesn't necessarily imply x independent of y given z. So there is no arrow in either direction in terms of implication. There was another question here.
Could you repeat the intuition about the fire?
About which one?
The intuition about the fire and the smoke.
Okay, let's put fire smoke alarm in this framework here. Fire, we thought fire might cause smoke, might cause the alarm to go off. And so a realistic assumption for a distribution over F, S, and A would be to say alarm is independent of fire given we know whether there is smoke or not. That would be a realistic assumption that would capture this causal reasoning pattern over here. Still a model. You know, you could have an alarm that goes off based on temperature, not just based on smoke and so forth, but this could be a reasonable model. Yes?
In the other time, like for just y, they were like associative. You said like the probability of x given y is the probability of x, and then the probability of y given x is given y. Is that also the same thing?
Okay, switch the roles of x and y. Yes. So, great observation. Equivalently, for all x, y, z, p, y given z, comma, x equals p, y given z. Absolutely. So we have three equivalent definitions for conditional independence, just as we had three equivalent definitions for independence. Yes? We'll see a lot of examples, and I think it'll become clear why these kind of reasoning patterns can occur. For now, I just want to make clear that there is no such implication in either direction. But we'll see examples when this pattern is indeed manifested where sometimes it will be the case, x and y are independent and also independent given z, sometimes not. And we'll see many examples. Any other questions? Yes?
What would be if they were not conditionally independent?
What would the formula be if x, y, and z are not conditionally independent? Okay, let's complete these equations. This is really important that you can do this quite readily. So, one example here, this would be equal to always, independent of the assumption, no assumptions made, we have px comma y can be written as px given y times py, right? And we just carry along the conditioning on z. So we apply this equation here, but we put a bar z in there everywhere, so we have this is equal to px given y and z, because that's what we're carrying around, times the probability of y, and again bar z because that's what we've been carrying around. That's always true. No assumptions need to be made for this to be true. If you make the conditional independence assumption, then this one here simplifies to this one here. and the y disappears behind the conditioning bar, which is exactly what we had here. And so by illustrating this, we show the equivalence of these two ways of defining conditional independence. In general, whatever rules you know of, where there's nothing conditioned on in the end, will still be true as long as you carry along consistently the same thing you condition on. Any other questions about conditional independence? Okay, so that's our building block for the next couple of lectures. Let's do a couple of examples. What we'll do here is we'll look at a domain, we think of a model for that domain, and see what conditional independence assumption could be reasonable to assume when modeling this domain. Whether there is traffic or not, whether you see people carrying umbrellas or not, and whether it is raining or not. What would be a reasonable conditional independence assumption here? Yes, over there. Umbrella and traffic are conditionally independent given you know whether it is raining or not. Why would that be the case? Well, intuitively, you could think about this as rain could be causing people to carry umbrellas, could be causing more traffic or less traffic if it's not raining. And so when you know the cause of both of these effects, knowing anything about the other effect doesn't tell you more about the first cause. So we have this conditional independence here where rain makes these two variables conditionally independent. Here's another example. This is our fire smoke alarm. Okay, a lot of people need to know this one now. What's the conditional independence assumption that we might be willing to make here? Okay, fire independent of alarm given smoke. Why? Because the pattern we observe is that fire tends to cause smoke, which in turn tends to cause the alarm to go off. And so once you know whether there is smoke or not, knowing anything about fire doesn't tell you more about alarm. Now, okay, it depends what kind of solutions your robots come up with. Now, what we'll start doing is this conditional independence thing is our building block, and the way we'll use it is inside the chain rule. The chain rule is this very general thing that always applies. If we have n random variables, we can instantiate the chain rule in n factorial different ways based on how we order the random variables. And for certain orderings, it'll turn out that we can instantiate these conditional independence assumptions quite nicely and get a simplified representation. So, how about traffic, rain, and umbrella? What's a trivial decomposition using the chain rule? Remember what it does is it starts with one variable going on here. No more pen. Chain rule starts with the first variable, x1, and the fact that it's the first variable is an arbitrary choice. You can number your variables whichever way you want, and says that the joint distribution is the product of the marginal of the first one times the conditional of the second one given the first one times the conditional of the third one given the first and the second one, and so forth. So you can write your joint as a product of conditional distributions. This gives you a trivial way of decomposing a joint distribution in a product, and one way to do this is over here. You have three factorial ways, so 6 ways of doing this for this particular domain. We picked one particular ordering. We said rain times traffic given rain times umbrella given rain and traffic. Now what we can do is we can start looking at our conditional independence assumptions and say, we said rain makes umbrella and traffic conditionally independent. What that means is that the conditioning on traffic here can just be left out, given we already conditioned on rain. What we end up with is an equation that looks like this. Why do we like this type of simplification? If you start counting how many entries these conditional probability tables have, the less variables you condition on, the smaller these conditional probability tables will be. And so if we can use the chain rule and get rid of a lot of things we condition on by making conditional independence assumptions, we can now represent the original distribution as a product of distributions, where each distribution that's participating in the product might have a relatively small table to represent it. And so you might be able to represent this big original distribution by a product of relatively small tables. That will be much more efficient than representing the original distribution directly, which we know for binary variables will be 2 to the n entries. Okay, so that's what we're going to be doing. This exact type of reasoning, we apply the chain rule, and then we say, oh, conditional independence allows us to get rid of some things we condition on, and that now gives us a more compact representation of this conditional distribution. Yes?
Can you think of it as partial ordering causation and effect?
So how does that relate to causation and effect? Our intuition for now will be that there's a very strong relationship. And if you order the variables based on how they cause each other, you will be able to cancel out a lot in the back of the conditioning bar.
Yeah, but the idea is like we kind of like have a partial ordering of causation and effect, and we consider children that maybe have parents in common, but like their children, there is no.
Yeah. So the suggestion here is to somehow draw a partial ordering of cause and effect, and that drawing might inspire what we can do here. And that's exactly what we're going to do. That's the graphical model we're going to draw. The thing you're thinking of is exactly what we're going to be drawing. Any other questions about this? Okay. So let's look at a simple application of this. This is back to Ghostbusters. The ghost could be in the bottom drawer or the top drawer. You have measurements. When you open a drawer, you get a noisy measurement of whether the ghost is actually there or not. So let's see, we have the ghost. One random variable is whether the ghost is in the top square or not, true or false. We have a measurement for the bottom square, a measurement for the top square. We could measure it as red or not. Red means that it's likely the ghost will be there. These are two independent sensors. So the way we're going to model this is as follows. We have a prior for the ghost, 50-50, and then we have a sensor model for the top drawer. So the model there is that 80% of the time when the ghost is there, we measure red. And 40% of the time when the ghost is not there, we still measure red. And a similar model for the bottom drawer. So notice that we just have a model for the marginal for the ghost and then two conditionals. And we're going to put those together in one joint distribution. So the way we put them together is as follows. This is not a general way of building a distribution over three random variables. Why not? If you apply the chain rule, there would have to be an additional conditioning here on T in the back. That was left out. Why was that left out? Because we made the assumption, the conditional independence assumption, that the measurement for the bottom drawer is independent of what you measure for the top drawer, given you know where the ghost is. It's reasonable. Your sensor for the bottom drawer is just measuring something about the ghost, not saying something about the other sensor. So making that assumption, we can then build a joint distribution, which in this case has 2 to the 3, which is 8 entries, from having just a small number of entries over here. If we had, let's say, 20 sensors that all worked independently just based on where the ghost is, we would go from an original representation of 2 to the 21 down to a representation that now would be 21 times 2. So what we see here is that instead of getting exponential scaling in the number of variables, we get linear scaling in the number of variables in how we can store a distribution by storing it in a factored way. Yes? The independence assumption we make here is that B is independent. Sorry, the drawing is not that fluent with this button. B is independent of T, given that you already know whether the ghost is in the top or the bottom drawer. Here you go. That's the assumption we make, and that's why here we just have a conditioning on G, rather than if you straight up apply the chain rule, you would get conditioning on G and T. Okay, what's the big picture for Bayes nets? The big picture is that if we want to deal with large numbers of random variables, representing the joint distribution in a table is very expensive, takes a lot of storage. Computing with it will be expensive. And the fact that you have a lot of entries doesn't just take a lot of storage, but coming up with the numbers in that joint distribution will be difficult. How do you come up with that many numbers that are good probability estimates? It's very hard to come up with a lot of probability estimates, especially if you only have a small amount of data. So we don't want to deal with that many numbers as the underlying representation for our distributions. What we'll do is we'll decompose these distributions over large numbers of random variables into local interactions. And by doing so, we'll have a much more compact representation. In the first 10 minutes right now, we'll do this in a very informal way. Just build some intuition. Then we'll make it mathematically more formal, and then we'll see a few more examples. So let's start with building some intuition. Here's an example of a type of Bayes net you could be interested in. You have about 24-ish random variables here. There is age, there is socioeconomic status, good student or not, extra car, vehicle year, and so forth. These are all random variables that a car insurance company could care about. And some of these random variables they might be able to measure from you. Others they might not. And so they might want to reason about, given the ones they're able to measure, what is the probability that you would get into an accident or damage your car in some other way, get it stolen and so forth. And based on that, they might decide on your insurance premium, because the probability of there being damage to your car will determine the risk they're taking by insuring you. And what we're focusing on here is the probability computation. And so this here models the interactions in a more compact way. It's saying that whether you have an extra car or not is only influenced by your socioeconomic status. Only directly influenced by your socioeconomic status. That's the only direct influence. Let's look at another one. We see that age directly influences driving skill, medical cost, senior training is needed or not, risk aversion, whether you're a good student or not. What is age directly influenced by? Just by socioeconomic status. No, the arrow is going the other way. Age influences socioeconomic status. The arrow is going into socioeconomic status. You guys are probably mostly inferred to be poor. Then mileage. Mileage influences directly whether you get into an accident or not. It influences directly whether you have a car of value. Maybe the value decreases quickly if you drive a lot, and so forth. So the idea here is that you look at all your random variables and decide which are the direct interactions that are the strongest ones, and put it in a graph. Here's another one. Let's say your car broke down, and there's a bunch of variables related to that, whether the lights are still working, whether the oil light is on or not, whether the gas gauge is pointing full or empty. You observe the car is not starting. Not sure what that means. Something about your dipstick. Your battery could be flat, no oil, no gas, fuel line blocked, starter broken, and so forth. There's a lot of variables here, and the assumption we make is, for example, that the battery flat directly influences that your car wouldn't start, but the fact that no charging is happening doesn't have a direct influence on whether your car starts or not, once you know whether your battery is flat or not. So that's the key thing here, is that certain variables mediate the influence of other variables, and you're looking for the ones that are the direct influence. And by doing so, you're not going to be connecting all variables, but it's going to be a sparsely connected graph. Okay, so what does this notation mean? The bubbles are random variables. Very similar to CSP graphs. The arcs are the interactions. and they indicate the direct influence. Formally, they will be encoding conditional independence. We'll see more about that later. But for now, they're direct influence. And so in the weather domain, we have just weather, one random variable. In the toothache catch cavity domain, we have 3 random variables. For those 3 random variables, we have the following graph, where we are saying that cavity directly can influence catch and toothache, but toothache doesn't directly influence catch or the other way around once you know whether there's a cavity or not. So for now, we'll assume all these arrows are direct causation. That's often the way you want to go. It's not always the case, and we'll later see what the formal mathematical assumption is that we need to make. Okay, coin flips. What would be the graphical model or base net for coin flip domain? N coin flips. So N independent bubbles, right? So something that looks like this, that's the graphical model because they don't influence each other. Whenever there's no influence at all, there will be no arrows, and you have absolute independence. How about rain and traffic? Natural thing to think is that rain or not will influence whether there is traffic or not. Okay, so it could look like this. You have rain and traffic. Complete independence has no arrows. If you say there is a causation there, you have a model with an arrow from rain to traffic. Both models are graphical models. One of them will be a closer match to the real world than the other one, but both are in some sense correct, mathematically correct graphical models. You'll want to pick the one that matches well with the real world. Okay, so you're going to prefer the right one because it allows you to reason about the connection between the two. All right, let's restart for the second half of the lecture. So first thing, remember P1, you programmed the Pac-Man to run a clever A-star search with some replanning to eat these food pellets as efficiently as possible. There was a contest at the end where you could submit your search algorithm, and then we'd evaluate how many steps it took your Pac-Man to eat all the food pellets. All right, let's see how the best students did. Sounds too good to be true. Places 4 to 10. Okay, we'll start as place 9 actually. At number 9, Yuxing Zhu with 290 steps. Congratulations. Is Yushin here? Anywhere here? Can you wave if you're here? Dance? Not here? At number 8, Ji-Yoon Oh, also with 290s. Ji-Yoon here. Let's see. Ji-Yoon's not here. Should we clap for people who are not here? I'm not sure. Number 7, John Do. Is John here? John's not here. All right. Number 6, Matthew Brown. Matthew here. No waving. Christopher Wierig at 5 with 287. Who is Christopher? We're not seeing him. This is getting really funny. Number 4, David Galbraith with 286. Is David here? This is a clean no attendance for our 4 through 9. Let's give them a round of applause anyway, in case they're watching it. Then, for third place, we have a second place tie. One of the two teams in second place is Zhenghao Qian and Pieter Shi Chen with 284. Congratulations. Are Zhenghao and Pieter here? Zhenghao? Woo! Are you Zheng Hao or Peter? Say it again? Peter? All right. 284. What did they do? Strategy was an anytime algorithm using a randomized greedy search, randomization in the breadth first search for nearest food. Probabilistic heuristic encourages Pac-Man to go to the nearest food located in the direction with the fewest food left. Let's take a look at how that runs. Cleaning the board in 284 steps. Nice. The other team in the two-way tie for second place with 284 is Town Vuong. Is Town Vuong here? Over there, Town, congratulations. Strategy, improved version of the closest dot agent. Exploit map having food everywhere, so search in each direction from Pac-Man for next food. Preference for food surrounded by more food and walls has a primitive alley detection. Probably has a primitive alley detection. Run UCS if all else fails to find the closest food. Let's see how that plays out. Not the same start. Nice. Then for first place, gold medal, Pac-Man eat all the dots, goes to Kevin Lindqvist. Do we have Kevin here? Congratulations. Strategy, avoid leaving small bits of food around. Cost function is linear weighting of standard deviation in position of remaining food and average range between pairs. I like it. Discourages small groups being left uneaten. Let's look at what that gives. I also have a feeling that this video just runs faster. All right, congratulations to everyone in the top 10. Number 10 was not shown due to a weird glitch in our script extracting the top 10, where Peter Chen appeared twice in the top 10, which didn't seem right to take away a spot from who was actually number 10. So we'll find out who the actual number 10 is next time. How do we break ties? Oh, we didn't break ties.
It was like 290 several times.
Yeah, maybe the script should have called them all 6. I like that suggestion. Don't worry about that. So let's do traffic again with a working pen. And let's build a Bayes net for traffic in a more complicated scenario. Traffic is the first variable. Put it in the middle because we don't know yet what else is coming. It rains. Well, we've already looked at that. Rain is for us modeled as causing traffic. Then low pressure. Actually, let's put things off to the side. Traffic, rain, low pressure. Well, that's something that could cause whether it starts raining or not. So low pressure will be up here, influencing rain. Do we want to narrow from low pressure to traffic? That depends on whether you think whether traffic is also caused directly by low pressure or not. We'll assume not. The roof is dripping. Roof is dripping. Let's have the direct causation be from whether there is rain or not. There's a ball game or not. Well, let's say that that's influencing how much traffic there is, and maybe the rain could influence it because maybe whether there is a ball game or not is influenced by how much it is raining. Cavity. Let's put that one over here. Okay, here's the canonical artificial intelligence textbook example of a Bayes net. This is the canonical example. Comes back the most frequently in textbooks. Alarm network. So what are we looking at here? The variables are burglary, alarm, Mary calls. So the scenario is that there could be a burglary or not. Your alarm could go off or not, based on that burglary. Then your neighbor Mary could call you, let you know your alarm is going off. Your neighbor John lives on the other side of your house, could call you, tell you your alarm is going off. And then there could also be an earthquake, which could also trigger your alarm to go off. So what's the Bayes net here? Let's see. Burglary seems to be something at the very beginning in this causation. It could cause the alarm to go off. John might call, Mary might call, and an earthquake could also trigger whether the alarm goes off or not. What I drew right here makes a lot of assumptions. It assumes that when Mary decides whether to call you or not, Mary only pays attention to whether your alarm is going off or not. Mary doesn't base that decision on watching through the window and seeing whether John is also making a phone call. Mary doesn't base the decision based on whether there was an earthquake. Those things don't come into play. You could imagine that's not very realistic, that Mary would make her decision also based on whether it was an earthquake and then maybe not call because it was probably the earthquake. Who knows? But we make a bunch of assumptions. What's important is that you understand the assumptions that are being made. The assumptions we make are shown here in this graph. And for us for now, this is direct causation. And we assume that if there's no direct arrow going into a variable from another variable, then the effect of that other variable is mitigated through variables that do directly go into the original variable. So for example, for Mary, the only direct influence comes from alarm and not from any of the other variables. Question there? Why doesn't B go to M? Why not adding this arrow? My best answer is sure, why not? All right? This is a model, and you have to look at what the real world is like and what assumptions you are willing to make. The one thing we keep in mind is that we always want to have as few arrows as possible, because that way you get a more compact model. And so now you just need to think, am I willing to not have this arrow? Do I need this arrow or not? If you think Mary might directly observe the burglary in action, right, then you want that arrow. Because Mary could see the burglar walking through your window or something, and based on that give you a call and say, hey, somebody's crawling through your window. That's possible. If you think that's an important factor, then you need that arrow. If you think that's not really that important, that's not going to be what's happening. Mary's just sitting somewhere closed in, and all she can do is listen to whether your alarm is going off or not, then you really don't want this arrow.
Is my logic wrong to think that B includes A, which includes M, but B includes that? Is that wrong?
The logic, whether B is influencing M or not in this model over here without this arrow, yes, B influences M through A. That's true. Just not directly. It's mitigated through A. Because B triggers the alarm potential, which then triggers Mary calling. Yes? There's two ways of building these graphs. One way of building the graph is to think about the domain, you write down the graph. That's what we're doing for now. Another way of building the graph is to already have a distribution, and then for that distribution, write down the graph that is compatible with that distribution. Both are valid. For now, we're starting from just modeling the world and trying to model it as a relatively small number of interactions. Yes?
So would it be correct to say that E, J, and M are all conditionally independent given A?
What you're getting at is that from looking at this graph, you can read off conditional independences, and that's absolutely true. And we'll next lecture study exactly which ones we can read off from looking at the graph. But that's the right intuition. You can read them off from the graph in many cases. Okay, so what are the exact semantics of what we have been doing? For now, we've said, let's draw this graph that reflects how we think of the world as variables causing each other. What does it really mean mathematically to be drawing these graphs and think of them as representing probability distributions? Well, we have a set of nodes, one for each variable. We draw a directed acyclic graph. That's a restriction. We're not allowed to have cycles. Then for each node, we look at the parents of that node and associate with the node a conditional distribution that is the conditional of that node given all the parents of that node. So that's the conditional distribution we store with a node. What is that conditional distribution storing? Well, we can think of it as a noisy causal process. Is the conditional of X given the parent values? If it were deterministic causation, then the entries in that table would all be ones and zeros. But if it's a noisy causation, then there will be non-zero and non-one entries in that table. That's the typical case. And so what you're capturing is this noisy causation process. The abbreviation we'll be using a lot, CPT, stands for Conditional Probability Table. There will be one for each variable. The Bayes net consists of both the graph and these local conditional probabilities. So there's two parts to a Bayes net. Yes? So in terms of notation, probably best to look at this one here. What this is saying is that this is a conditional probability distribution. It's actually a set of distributions where you have a distribution for every possible combination of instantiations of the A variables. So if they're binary, there will be 2 to the n possibilities. Like this will take on 2 to the n different combined instantiations. And so you'll have 2 to the n conditional distributions for X. One distribution for each combined instantiation. And so yeah, if X were binary, then there would be 2 entries per conditional distribution times 2 to the n distributions in this conditional probability table. And from this size here, you can see that you'd like to have Bayes nets where the number of parents is relatively low. Because if the number of parents is relatively low, then this n here will be low, and you'll have compact representations of your distribution. Yes? What is? A net? Net is a shortcut for network. Just Bayesian network or Bayes net, it's just an abbreviation. BN is another abbreviation we'll use. Really what it is a directed acyclic graph in our context. Okay, so that's the base net semantics. Once you have a graph, a directed acyclic graph, a conditional probability table for each variable, you have a base net. Once you have the base net, you implicitly encode a joint distribution over all variables in the base net. How do you find the distribution? You just multiply all these conditional probability tables together. This equation here tells you how to get from the base net the joint distribution. That's one thing to keep in mind. Even though you start with something very compact, you can always back out the much more expensive full joint distribution table. It's always encoded. You can always back it out from it. All right. So here's an example. Cavity, toothache, catch. What are the conditional probability tables? We have PC, P catch, and P toothache. Sorry, P toothache, given cavity, P catch, given cavity. These are the three tables. And to get the joint, we just have to multiply all three of these together. We get the joint distribution. So if we want this particular entry here, this will be equal to the probability of plus cavity, which we read out of here, times the probability of plus catch given plus cavity, which we'll read out of here, times the probability of toothache minus toothache given plus cavity, which we will read out of this one here. So that's how it works. Any probability, joint instantiation, you can compute the probability for the joint instantiation by multiplying the corresponding entries together. Okay, now the mathematical question. Why is this true? Why is it true if we define this base net concept? You know how to define them. Why is it true that if you multiply everything together, that you get a joint distribution over all the variables? Right. We know to have a joint distribution over a set of variables, it needs to be the case that all entries in that table need to be between 0 and 1, and they need to sum to 1. If that's not the case, you don't have a proper joint distribution. So why is it the case that if we follow this procedure, we find a proper joint distribution? Okay, let's look at how we can derive this. We know something that is true for all distributions. It's always the case that we can apply the chain rule, and we can write the joint distribution as a product of conditionals. Okay, always true for all distributions, and also for all orderings. Then we assume conditional independence. What do I mean with that? We assume that the conditional of xi, given all preceding variables, is the same as the distribution for xi, given just the parent variables of xi. If we assume that, then we can simplify the expression we had in the chain rule, and we can remove some things from behind the conditioning bars and reduce it to just the parents. And so we get this over here. So what this is showing is that if you draw a graph, a directed acyclic graph, compatible with the ordering of variables in that graph, you can index your variables 1 through n. You apply the chain rule, which is always valid. Then you make this assumption here, you get this expression over here, which is how we define the joint for a base net. So formally what this is saying is that the assumption we make about our distribution when defining it in the form of a base net is this assumption over here. That is the assumption we really make. We don't make an assumption of causation. We don't. Nowhere do we say there is a causal process here. To make the math work, all we do is make this assumption, which is n assumptions, one for each variable, that the conditional of the variable given all the preceding ones is the same as the conditional of the variable given the parents of that variable. That's the assumption we make. Causation was just a way for us to build intuition. And when there is causation, often you can have a very small number of parents And you can get rid of a lot of things behind the conditioning bar, but that's just a coincidence. That just makes it work out well. But mathematically, this is the only thing we assume. If we're willing to assume that, then we can build a joint distribution from any base net that we put together. Any questions about this? All right, so now we know why it works to define base nets the way we define them. What is the trick in defining base nets when you draw these graphs? The trick is to get small conditional probability tables. So what that means is the trick is to somehow order your random variables in a way such that when you look at your variable xi, conditioned on all the variables you already put in your base net, that somehow you can get rid of most of them and have a very small number of parents. That's the trick. So when you model a real-world domain, this is what you keep in mind, and you somehow, if you order your variables in a causal process, you'll see that very often this works out really nicely. Example, coin flips. We now know how everything works. What's a probability distribution? Here, the joint distribution entry for HHHTH. Straightforward. Just multiply the separate CPT's entries together, right, to get the joint. In this case, it looks like that, where here we have H, H, T, H. This will work out to be 0.5 to the 4. This demo here, we're going to do next time. What we'll look at is we actually have a BaseNet toolbox that you can play around with. It's a web demo where you can build your own BaseNets from scratch and run algorithms in it. Let's do another example. Traffic. What is the probability for plus r n minus t to happen? Well, that's the probability for plus r times probability for minus t given plus r, which we can then compute, plus r 1/4, minus t given plus r, also 1/4, so 1/16. Alarm network. What would that look like? This is just the directed acyclic graph, including the tables. Looks like this. Why is this one the biggest table for alarm? Because alarm has the most parents. Right? The more parents you have, the bigger your table will become. Okay. Now, I'll kind of get back to what we just talked about. What does it mean to define a BaseNet? What is the assumption that we're making? Let's look at an example that might be a little bit of a mind twister initially. Rain and traffic. So far, we've always thought of rain as causing traffic. Then when we build the BaseNet, we start with rain. That's the first variable. It just needs a table for itself. Next variable is traffic. Needs an arrow from rain to traffic. We have a conditional distribution there. What we can do is we can multiply these entries together, the corresponding entries, and recover the joint distribution for T and R. But somebody could say, this BaseNet procedure nowhere refers to causality. It doesn't. It's just an intuition we have. It's often a good intuition, but it's not the math. So according to the math, you could just as well start with traffic. Nothing wrong with that mathematically. Might be less intuitive, but the math is fine. So what you could do is you could say, let's reverse this. Let's assume traffic causes rain or not, right? Keep in mind, though, that we're not really talking about causation. We're just doing math. And we say we first pick T, put it in the BaseNet. That's the first variable. Then R. And we put an arrow from T to R because there is a relationship between T and R, right? When we enter R, we have to ask the question, is PR equal to PR given T? And the answer is, typically you would say no, because they're not independent, so you want to keep that arrow from T to R. So what are the tables now? Well, you could measure how often is there traffic, right? That'd be your first table, and then you could measure how often there is rain, when there is traffic, and when there is no traffic, and build a table that way. Now you can do the same thing as we did before. You can take these two tables, you can multiply them together, the corresponding entries build the joint distribution. This is our joint distribution for T and R. Now, the thing we have to keep in mind here is that when we build a Bayes-net, what we are doing is building a compact representation for a joint distribution over a set of variables. That's all we're doing. We did this in two different ways, and now let's compare. 3166 over 16. So let's think about that. 3166. Let's go back. 3166. Same numbers. So what you're seeing here is that even though the graph looks different, the tables we store are different, the joint distribution is still the same. And we didn't even follow the causal process here. Even though we think of this as causal, we didn't follow that process. We ignored that intuition. We just followed the math. And here we are, and we have the same joint distribution. So this is something really important to keep in mind. The causality is nice to have. It makes it easy to draw the graph. But mathematically, all you ever have to think about is come up with an ordering of your variables, 1 through n. Once you order them, work through them one at a time from 1, 2, 3, and so forth, and check what assumption you are willing to make about the conditional of xi given the ones that precede xi. That's all you need to do mathematically. And then you have a Bayes-net as the product of all these conditional distributions. Okay, so what about causality? Is there still something useful to be had there? I'm going to take your question later. Something useful to be had there still? Well, often when you go through this process of looking at Pxi given x1 through xi minus 1, and you're wondering which ones should I be making the parents, which ones can I leave out? If you have a causal process, often you can leave a lot of them out. You get a very small conditional probability table. So there's something there. In principle, you could go work through all n factorial orderings and for all of them see what you end up with, but that's a lot of work. And so one intuition could be the ordering I'm picking is the one that's closest to causality, because then often it works out well. Often it's easier to think about the reasoning patterns in the Bayes-net whenever it's causal. And often it makes it easier to get the numbers from experts. Like, go back to this table here. If you ask somebody, what's the probability of rain given that there is traffic? That's much more difficult to come up with than the other way around. The other way around is a causal process. You can think of, well, traffic will probably increase the probability of rain. Rain will probably increase the probability of traffic by this much. That's something you can reason about. The other way around, just like when we saw Bayes' rule, typically one direction is more easy than the other direction. So that's why causality can be useful. They don't need to be causal. And sometimes there is not even a causal direction to it. What if you just had two variables, traffic and dripping? Because you got rid of the rain variable, which caused both of them, you now have no way to choose a causality direction here. And so you'll just arbitrarily pick an ordering. You pick T first or D first, mathematically no real difference, we know that. You'll pick one of them first. If we pick T first, it'll look like this. If we pick D first, it'll look like that. So keep this in mind. The arrows encode conditional independence, and it's this particular assumption over here that is encoded by the arrows. So I know there are a couple of questions left. I'm going to take those after lecture. I want to just conclude here and foreshadow for next lecture. So far we've seen how you can build a Bayes-net, by drawing a graph, putting conditional probability tables with each variable. Next, what we're going to look at is try to understand what assumptions we made implicitly. We made these assumptions very explicitly, but we now have this sparse graph. Are there any other conditional independencies that are implied by our graph? And can we read them off directly from the graph? That's what we'll look at next lecture. So we'll formalize those ideas of how do you find independencies from looking at the graph. After that, we'll start looking at numerical queries, where you say, given a certain set of variables have been observed, what is the distribution over another set of variables? Without having to go to the full joint distribution, because then we build this big table and we're back to where we started from. All right, that's it for today.